Hello. Good afternoon, everyone. Thanks for having me back to talk about Ethernet speeds. I showed this picture a couple years ago, but I'd like to open with this because it's pretty cool. This is a diagram that the original Ethernet inventors drew about 40 years ago at Xerox PARC. And I think it's cool because it turned out they got a lot of things right. And Ethernet is definitely the predominant networking technology that we have across wireline and wireless infrastructure today. So I think that's pretty amazing that they drew this 40 years ago. There's a lot of stuff going on with Ethernet, so I wanted to give you an update at all the different speeds that we're developing and talk a little bit about the market development first. This is a roadmap that was developed by the Ethernet Alliance, and if you follow the link at the bottom of the page, they have a bunch of cool PDFs and graphics there. But what we've seen is that there are a bunch of new different market requirements that we're seeing in terms of speed, distance, and cost, and these are driving requirements for a variety of different new speeds, and I'll tell you about all these in detail. But primarily we have wireless access points that are driving a speed for 2.5 and 5 gig. We have servers that are driving a speed for 25 gig, and then we have core networks that are driving a speed for 400 gig and higher. And the interesting thing is that we have the possibility over the next 5 to 6 years to have about 6 new Ethernet speeds available on the market, and this is as many speeds as we've had in the past 30 years. So there's definitely a whole lot of development going around Ethernet. The target applications, 10 gig obviously is pretty widely deployed, and we see that everywhere in the network. The needs for 2.5 gig are driven largely by wireless and a very large installed base of Cat5e and Cat6. 25 gig is a new speed designed for servers and data center aggregation. There is more interfaces for the 40 and 100 gig speeds, and then we're also working on 400 gigs as a new core technology. All right, let's talk about each of these in a little bit of detail. 2.5 gig and 5 gig, there's two drivers. The main one is high-speed wireless. We have wireless speed now that exceed the wired speed. So with 802.11n, we had about 600 megs on the wireless side. Now with 802.11ac and possibly with .11ax, we're seeing speeds in excess of 7 gig and possibly 4 times faster. The rule of thumb is that you need about 75% of the wired speed to the radio speed, so that translates pretty directly into a requirement for 2.5 gig and 5 gig on the access side. Higher wire speeds are available, but I'll show you this on the next slide. They also require a different type of cabling, and they may or may not support PoE, so that's a requirement to drive the access points. In terms of the other drivers, the large installed cabling base, and I started pulling Cat5, I think, in the early 2000s, so even before this study was done, but the IEEE used a study that was done from 2003 onwards to 2014, and this study alone cites that there were 58 billion meters of Cat5e and Cat5.6 installed. That translates to about 1.3 million outlets, so you can see that's a huge amount. If you think of every building that exists in every city in the world, every hotel, every office building, every apartment building, every school, they just have a huge install base of Cat5e and Cat6, and we want to use those for higher speeds. So there's technology available like 10G base T or 25G and 40G base T, but they require different types of cabling, and they don't have the distance to go up to 100 meters on Cat5. There's other applications. Wireless is the primary driver, but the IEEE cited applications for higher desktop speeds, small cell, high-def security cameras, so pretty much anything that can use a higher access speed than a gig. So that leads us to the IEEE.3BZ task force. It was just started last March, so a couple months ago, and they have their first meeting next week, so there's not a whole lot to report about it yet. They have defined 3 speeds that they're working on. The first one is 2.5 gig over 100 meter Cat5, and then there's also 5 gig over 100 meter Cat5e and 5 gig over Cat6. It also includes PoE support, including the 4-pair amendment, so this is especially important when you're trying to get really high power up to 60 watts on PoE. And you can see the task force webpage at the bottom if you want any more information. And we expect the standard to be pretty soon. The lower speed standards are going really fast, primarily because it's just reuse of existing technology. So we expect standard in 2016 and also interfaces in 2016. There are 2 industry study groups that are also behind the 2.5 and 5 gig Ethernet efforts. The first one is the MG-based-T Alliance. This is one, as far as I can tell, driven primarily by Broadcom, and then the N-based-T Alliance, which is basically everyone except Broadcom. So it's interesting to see how these 2 groups will influence the standards. Broadcom has already published a proprietary spec based on NG-based, so I'm sure that'll be used to influence how the standard works. All right, moving on to 25 gig. The market driver for 25 gig is really to provide two things. One is a server connection speed that's really optimized for cost, throughput, and efficiency, and also to maximize the efficiency of the server to switch interconnect. And I have some math on the next couple of slides that'll show you that. Using single 25 gig lane actually gives us a lot of advantages, and we're already using 25 gig all over the place. We use it for 100 gig. We use it for the Cowie-4 signaling, which is the signaling between the optical modules and the ASICs. We use it in the optical modules themselves. We would like to do 100 gig to 25 gig breakout. The 4 breakout is very popular. So 25 is kind of the new 10 if we look at the electrical signaling that we have to work with, and we expect to see quite a few developments around 25 gig technology in the future. And then you say, well, what about 40 gig? Wasn't there this whole thing in the IEEE where we were going to do 100 gig, and then we added 40 gig, and no one liked that, and there was big confusion about that. So yes, that's true. 40 gig in comparison by now is already 8 years old. When we were working on the technology, it was standardized 6 years ago, so the technology has come quite a ways since then. It uses inefficient 4 times 10 gig signaling in comparison, and it also has the higher cost and larger QSFP plus optic in comparison to the QSFP28. And then the bottom line again is that there's just different market requirements. So there's a market requirement for 40 gig, and there's also a market requirement for 25 gig. The interesting math is that there's going to be a bunch of 3.2 terabit chips coming out on the market this year that'll be shipped by vendors. So if you do some math just using 3.2 terabits kind of as a switch ASIC capacity, you can see that if you use a single lane of 25 gig, you get much better efficiency in terms of the port density and also in terms of the fabric utilization. So if we used 40 gig with 4 times 10 gig signaling, in this example, it's 28 servers and 400 gig port uplinks. We only get about 50% utilization on a capacity of 3.2 terabits. Now the interesting thing is that if you're building a very large, like a hyperscale sort of data center with 100,000 servers, and you try and connect all these with the top of rack switch, you can see that you need about 2,500 less switches if you use 25 gig versus 40 gig. So that's a pretty substantial difference in CapEx and OpEx. And the other table that shows just some straight math if you have a number of ports with different lanes of signaling, so you can see that with 25 gig signaling, you can actually get 128 usable ports on a 3.2 terabit ASIC with 100% utilization. So that's really what's driving the math behind that. In terms of developments, there's a lot going on with 25 gig. The 25 gig G-based study group, they actually combined their meetings with the existing 40G based T task force, so there's going to be one standard. They just kind of slid those two standards together. There's no change in the schedule or anything like that, so .3BQ will have a standard for 25G and 40G based T. And then there's also the Ethernet task force, which is working on 4 different objectives: a backplane Ethernet, 3-meter and a 5-meter copper cable Ethernet, and also a 100-meter multi-mode interface. They're already well underway. There's the first draft generated, and like we saw with the 2.5 and 5 gig, we're going to see the standard sometime next year, also with interfaces sometime next year. There's the 25 gig Ethernet Consortium. This is an alliance that was founded by a few key market players, and they're developing 2 standards outside of the IEEE, a 25 gig Ethernet and also a 50 gig Ethernet standard. The specification is worded kind of very specifically strangely in that it's only for backplane and twin-ax copper, but does not address or preclude active cabling or some sort of fiber interface. So the standard, unfortunately, is only available to members, so I can't tell you what's in it, but I think the read out of here is that we're probably going to see some fiber interfaces that are longer than 100 meters that'll go on single mode for 25 gig. Here's a technology reference slide. I have these for each of the Ethernet speeds. I tend not to read them at conferences, although they're very, very, very interesting. If I read them to you, they're also very, very boring, so I don't want to put the audience to sleep. The one thing I will mention about 25 gig Ethernet is that we have this new thing called the SFP28. It's the same size as the SFP or SFP Plus for 1 and 10 gig, and it just lets us do 25 gig Ethernet. And that's basically what everyone's using for 25 gig. And I'll just skip over the technology references in the next sections. All right, moving on to 40 gig. 40 gig is pretty good as far as the market's concerned. We have the QSFP Plus, we have a bunch of interfaces. It's very popular for 4 times 10 gig aggregation in data centers, so we have a bunch of copper and fiber breakout options. If you want to do native 40 gig, we have a bunch of different standards available now. The one that was just developed in earlier this year is the ER4, so we can get up to 40 kilometers on single mode for 40 gig now. And that's about all that's going on with 40 gig. As I mentioned, there's also 40G base T, which is combined with 25G base T standard, and we'll see that sometime next year. And that's about all that's going on with 40 gig. It's pretty much done and usable and deployable now. Here's your reference table that I'll skip over. And moving on to 100 gig. So this is a slide that's worth spending some time on because we're at the kind of the turning point in the technology adoption. If you look at market adoption of a technology, turns out, and I actually learned this is the one thing that I remember from my statistics class a long time ago, but everything turns out to be a bell curve, as with anything. And if you look at how technology is adopted, it's adopted as a bell curve. So this is anything. It could be vacuum cleaners or iPhones or you know, I don't know, new sweatshirts or something, but there's always some sort of innovator and early adopter market, then it moves into majority, and then there's the people that adopt it last. So in terms of 100 gig, we're crossing the chasm. The chasm is what's between the early adopters and the mass market. So we're about to cross the chasm with 100 gig. I thought we were going to do it last year, but I was wrong about it. This year, I think, it is going to be the key trend. There's 2 things driving that. There's the smaller optics, and I'll tell you about those in more detail in a couple minutes. That's the QSFP28 and the CFP4, and there's also the ASIC that I mentioned, so the 3.2 terabit ASICs that can now support up to 3,200 gigs on a single line card. So that's driving a lot of adoption. Next year at Del Oro, which is a market analysis group, they project that we're going to ship 100 million Ethernet ports. So does anyone know how many ports we shipped last year? It was 17,000. So it's quite a big difference. And then in the next couple of years, we'll see, you know, as any market develops, as we saw with 1 gig and 10 gig, we'll see a bunch of different options come along as we have the technology. I just put something like a theoretical 100 gig SFP. We don't have that yet. No one even knows what that's going to look like yet. But over the next couple of years, something like that will come along. That'll give us much higher density commodity ports. Okay, first generation 100 gig. Some of you may have already seen this slide, but the fundamental challenge that we have is that the first generation 100 gig used a lot of 10 gig signaling. That's just because that's the technology that we had to do that. As the 25 gig technology develops, we'd like to incorporate that into 100 gig to make it faster and cheaper and higher density. So that's what we're doing now. You're seeing a lot of the 10 gig components are now moving to 25 gig on the electrical and on the optical side. In terms of developments, there's not a whole lot going on. There's a short reach interface, 100G based SR4 that was developed. The important thing really is the electrical signaling, so that's the COWI4 signaling. That's using 4x25 gigs. There were 2 objectives that were in the standard that didn't make it. The first one was a 20-meter multi-mode interface. That one was just removed because it didn't make sense. We already have the 100-meter interface. There wasn't a whole lot of difference or advantage over that. And then the one that we really needed but didn't make it was a medium range single mode interface. So right now for 100 gig, we don't have anything between 100 meters and 10 kilometers. We have a 2 kilometer standard, but not anything for short reach that's optimized for 25 gig signaling. So that unfortunately was taken out of the IEEE due to lack of consensus, and I'll show you how that affected things on the next couple slides. In terms of the module evolution, if you remember the first CFP was kind of large, kind of clunky, and expensive in terms of power and also in terms of cost. They were massively expensive, sometimes you know, as expensive as a line card. But over the evolution of the generation, just as we had for 10 gig, you know, 10 gig started out as a very large 300-pin MSA fixed port back in 2002 when it was developed. And then we went to ZenPack and XFP and SFP Plus. Same thing's happening with the 100 gig market. So we started out with CFP. Now we're moving to second generation. And as I mentioned, the important ones are QSFP28 and CFP4. Those give us the really high density that we need in order to do high density line cards combined with the ASIC technology like the 3.2 terabit ASICs. So that gives us the full port capacity up to 22 to 44 ports with the QSFP28 or 16 to 32 ports if you put them back to back with the CFP4. Module evolution. Here's just a different graphic for you, and especially, it shows you in relation to an iPhone. I think this is probably one of the more important slides. Everyone wants to know, how big is this thing? You can see that the CFP is actually quite large. It's larger than an iPhone. CFP2 is about the size of an iPhone, getting smaller. Then the CFP4 and the QSFP28 will, be about the size of an XFP. Not quite down to an SFP plus size, but definitely the size of an XFP. So it's getting smaller. This is what happens when we don't reach consensus in the IEEEs. We have a bunch of MSAs. So an MSA just means multi-source agreement. It's a bunch of people getting together and deciding to do a standard. There's nothing wrong with that. The IEEE Ethernet standards are written so that other standards can be developed alongside of them. The problem is that if you remember for example, VHS versus Betamax or something like that, is now we have 4 different VHSs versus Betamax and not just 2. So when 100 gig first came out, we had the 10 by 10 MSA standard, and that was to really provide an alternative because the IEEE didn't have a short reach single mode interface. So the 2 kilometers is very popular. The 10 kilometers is popular because it was cheaper than the IEEE standard ER4. But now for the new generation, we have 4 MSAs that are doing a short reach single mode interface, and in fact 2 of them are doing the same thing, but they don't interoperate, and they're all driven by different competing vendors and different competing standards and different competing objectives. So it's going to be interesting to see what plays out in this market, but we definitely can't sustain new IEEE interfaces as well as all these 4 MSAs. So someone's going to have to lose, unfortunately, and the market's just going to have to decide that. Here's a technology reference slide. So moving on to 400 gig, and this is where it gets really hard. So for 10 gig, basically all we're doing is we're blinking a light. We're just blinking it faster than 1 gig, but that's basically it. 100 gig and especially 400 gig, this gets into really complicated DSP, digital signal processing. You have to do a lot of proprietary modulation and a bunch of complicated stuff so that we can actually get this technology to work. In the IEEE, we realized that Ethernet at terabit speeds is today not very practical from a technical and an economic perspective, but we know that terabit links are needed soon in core networks. So, we would have loved to do terabit Ethernet. I think it sounds really cool, but it's just not feasible. And the challenge here is that if we make something that no one can buy, then we failed. If we make something that people buy and then it doesn't work, then we failed too. So the economics are really difficult here, and we have a bunch of different things to consider in terms of the electrical and optical signaling technology that we have, the optics form factor, balance versus all the market requirements. So there's a bunch of different market requirements that we have to take into consideration, and the IEEE really provides this open forum and lets the economics dictate the solution. So that's why we couldn't come to an agreement on the 100 gig standard that I mentioned for 500 meters, because there's just, there's no obvious good solution, and we had to pick one, and we couldn't pick any. So the next higher speed is going to be 400 gig. There's a link to the IEEE bandwidth assessment ad hoc, which studied the market and determined that 400 gig sounds like a good objective just based on the technology and the speed requirements that we have. So the task force has been going for a couple years. They're working on four interfaces and an electrical specification. The first one's already defined. It's 400G based SR16. It's going to be 16 times 25 gig parallel over 16 parallel multi-mode fiber links. And then the longer reach objectives get much harder, and I'll show you that on the next slide. We've also defined the important electrical interfaces. There's a 25 gig and a 50 gig electrical interface. As 40 gig and probably 100 gig will be very popular, we also want to support the 4 times 100 gig breakout, so that's a very useful application. So we see the standard and interfaces probably available in about 2 years from now. This is the problem with the single mode interface, is that there's no real clear technology winner, and everyone has a different proposal, and everyone in the IEEE has their preference on technology. So there's for the short reach interface, like I said, it's pretty much done. It's 16 times 25 over multi-mode. But as we get into longer reaches, we see that NRZ is not really feasible for higher speeds anymore. And so we get into different modulation speeds like PAM4 and DMT. We can do those in a number of different ways. There's basically 4 ways to go faster. You can just go faster. You can change your modulation, you can change the number of lambdas, or you can change the number of fibers, or some sort of combination of that. And that's the tricky thing, is to figure out which combination of speed, modulation, fibers, and lambdas gives you the best economics and the best technical feasibility. So this is the big discussion in the IEEE, and I expect there'll be a lot of debate next week in the meeting about it. If you look at the module evolution, we'll see the same thing as we did before. There's going to be first generations, which are already pretty well defined in terms of the CDFP style 3 and also the CFP2. The CFP2 is the same module that we're using for 100 gig. We can actually run the signaling at 50 gigs on the electrical side, so that gives us 200 gigs. And then, as the technology becomes available, we'll see some sort of evolution in the next couple years into some sort of theoretical CFP4 or QSFP 100 or whatever. Like I said, those modules don't exist, but we know that they're coming. And that's really when Ethernet at terabit speeds becomes feasible, is when we have this 100 gig electrical signaling. So if we look into the future, we know that Ethernet is continuing to evolve and to meet new markets. We know that different speeds are required for new applications. And we kind of have to get our heads around that this old 10x, 3x model isn't going to work anymore. So we used to have the thing where we had a 10x performance for, the goal was 3x the cost. It wasn't 3x the cost, initially, obviously. But the new technology came down to 3x the cost eventually. But we went from 10 meg to 100 meg, 1 gig, and in nice 10x increments. But that really doesn't work anymore. So it turns out that the best increment, or the building blocks and the speed multiples now, are really 4x the highest lane rate, or maybe 8x the highest lane rate. So that's why we get to 400 gig. That's why we get to 4x25 for 100 gig. And then in the future, as we've gone from 10 gig electrical to 25 gig electrical, 50 gig electrical is the next speed that we'll see, and that could be the basis for some new technologies based on multiples of 50 gig. So it's likely that we'll see a 50 gig Ethernet and then some sort of 200 gig Ethernet, sometime after that. So if we wanted to sum it all up, here's basically a summary. We have 2.5 and 5 gig coming for higher speed wireless and Cat5e and 6 applications. 10 gig is very widely deployed. 25 gig is coming soon for server and top of rack applications. 40 gig is pretty popular in the data centers now, especially as a 4x10 breakout. We're squarely in the middle of second generation technology with 100 gig, and that's the CFP2, CFP4, and QSFP28. We're still a ways away from 100 gig serial signaling, but that'll come eventually. We're working on 400 gig Ethernet, and that'll use a lot of the 100 gig technology as a building block. And Ethernet at terabit speeds is still not feasible in the next couple of years, but we'll get there eventually. And it's probably, it's likely to be some sort of multiple of 400 gigs. So 1.6 terabit comes to mind as that using that 4x multiple math. More information, you can go to the IEEE web pages or the optics manufacturer web pages and get all the standards there. And that's about it. I have a ton of reference slides that are next, so feel free to browse those in your spare time, but I don't have time to go through them all. And that's it. That was a lot, I know. Any questions?
Okay. Any questions for Greg? That's all very clear. Any suggestions from the operational side, how these may come into life? Yes, I see a gentleman moving to the mic.
Good afternoon, Martin Levy, Cloudflare. This is all good, but it's still 1,500 bytes for every frame. Can you talk about this?
Thanks, Martin. So I think you said that at Apricot to me last year, and I didn't have a good answer. So I'll just repeat the answer that I said, but there's very little to no interest in the IEEE in standardizing a larger frame size. And that is because of the massive, you saw over 40-year deployment of Ethernet technology that could be possibly uninteroperable or could have interoperability issues if we increase the standard frame size. So every IEEE specification always starts out with, preserve the 1,500 byte frame size, and I don't see that changing, to be honest. But I agree that it's a problem.
Rüdiger, yeah, go ahead.
Rüdiger, Volk, Deutsche Telekom. Marty, thanks for starting with that question. And I would have phrased that like, well, okay, you were talking about the IEEE is seeing market demand for something, and do I understand you right that the IEEE is not seeing a market demand for larger frame sizes? Okay, fine.
Yes. So
The other unfollowing remark is you were referring to the 40 years of deployment. Unfortunately, I'm too young to have been to have enjoyed 40 years ago. I enjoyed about 30 years ago installation of yellow wire, if you know what that is. How much of the technical characteristics of Ethernet of 40 or 30 years ago actually remains in what we are doing today?
So that's a good point. By that I meant more in the intellectual property, and that everyone has ASICs that are tuned around these 1,500 bytes, and people are very hesitant to change that because it's been there for so long.
Well, okay. The nice answer to my question could have been, yes, we learned that data grim wins over circuit. That would have been a good answer. The answer that everybody has optimized their ASICs for 1,500 byte, I doubt. The large routers that I'm working with seem to do very well with larger, and I don't think that the vendors of that equipment count as nobody.
I agreed, because I work for one of those vendors. So I definitely agree. Yeah. So I think my point would be, if this is important to you, then talk to your vendors and let them know that jumbo frames are important, because the message is not getting through between the users and the people that make the standards.
Jeff Houston, APNIC. What's the minimum MTU size for this 400 gig or terabit specification?
The minimum frame size, it would be, 64 bytes.
So that means at a maximum rate, you're going to get a packet every 6.7 nanoseconds. So 0.67 nanoseconds, yes? Yes.
For 400 gig? No, it was 1 point something nanoseconds, right?
It's 1.3 for 400
Yeah.
or so. It's 0.67 for a terabit. What's
Yes.
the fastest memory you have?
Good question. So that's a whole other presentation. In fact, I just gave one about 2 weeks about it, about memory speeds. So yes, and of course I saw your presentation at Apricot. So good question. The challenge is really that the memory speeds have by far lagged behind the packet rates. So as Jeff mentioned, 100 gig, it's one packet every 6.72 nanoseconds. 400 gig, it's about whatever that is divided by 4, I forget the math. The random memory read rates are in the single nanosecond range. So we can get down to a couple nanoseconds, but the packets are coming in faster. Yeah, so good question. What that means is we have to buffer, we have to do a bunch of tricks because we can't look up the destinations faster than, or as fast as the packets are coming in.
And you've got no other answer at this point? Cool.
That's in my other presentation. But yeah, good point. Good point. The point I think is that we need, there's a bunch of different things in play here. There's obviously the ASIC capacity, there's the line rate, there's the memory capacity, and all those speeds have to increase, at the same time in order for us to do faster Ethernet rates.
Yes, 3 more minutes.
Sorry?
Go ahead. You have 3 more minutes. We can take another.
Benedict Stockerband, Stepladder IT. It's not just the memory, it's also the TCAM or whatever, because you transfer the problem into layer 3 where it's really painful.
Yeah.
Basically means you can get all the line speed you want, but if you can't route it, it's completely useless. So we really have a problem there.
Yeah, you're absolutely right. By memory, I meant lookup memory, buffer memory, any memory that's used in a router to forward packets has to be able to keep up with the line rate coming in. And it actually gets even harder because in a lot of cases, you may have to do multiple lookups per packet. So we can't even do all the lookups that we need in one clock cycle. So it's actually, multiple, cycles of nanoseconds that we need to look up a packet. But fortunately, the buffer memory is keeping up with it. So we can store the packets long enough while we're trying to look them up.
Any other questions? Well, thank you, Greg.
Okay, thanks.
I think we just recruited another talk for the next RIPE meeting as we speak. Thank you. Next in line, we have Greg Shepard.